Hello everyone. So this is again the next series for the interview sessions for in embedded systems. So today I will discuss with you about the protocols. Okay. So actually in embedded system you have different ICs that communicate with each other using some specific protocols like I2C, SPI, and UART. So also these are the three major communication protocols that will be asked in the interview for embedded system. So I will be going through it from the interview perspective, and it will be in three phases, three videos, one for I2C, one for UART, and another for SPI. So if you have a doubt or something, you can put it in the comment, I will clear it. Okay, so let's first start with the I2C. So first thing, I2C is inter integrated circuit. It means, so if I say that you have two ICs and now you want to communicate with them, so it's like if I say you have one IC and another IC is there. Maybe you can say that this is something which gives you the temperature of a system, and this is the IC which is your main controller. Now this temperature will be transferred to the main controller via some protocol. Like you will not write a logic to calculate the temperature, this IC will in turn give you the temperature. So this has to communicate with your main MCU via some protocol, right? So it's similar to as anyone communicating with English, Hindi, or Marathi, any language. So it's like over what protocol you are communicating. So mostly this kind of ICs will communicate over I2C. Now why I2C? First thing, it's a low power device. It requires very low power, and second thing is it is a two wire communication. That's why mostly the inter IC communication are over I2C. That's why the name is also there, inter integrated circuit. So it's between the two ICs. So first question in the interview will be on what is I2C. So I2C is a two-wire protocol that is that happens in between the two IC. Okay. Now let's just understand what all the protocols are. Now let's see what is there. So first thing is, you see here you have one master and there are three slaves. So it is like I2C is a two wire. There will be two wire and there will be a master. What is a master? I can say that master is something you can say is similar to as the main controller. So if the main controller requires some data, I will say it as master. So master is the main controller. If main controller requires some data, it will ask the slaves that are connected over this I2C. Okay. So first thing, I2C is a protocol that works with a master slave ideology. So there will be a master that will be controlling the entire bus, and there will be slaves which will be responding to the master. I hope it is clear. Now there will be two lines, right? So one will be SDA for the data and another will be for the clock. Now you will say data, I understand that something has to be sent, so there is a data line, but why clock, right? So clock is required to understand whether it's a first bit or a second bit or a third bit. Now I will show you why it is actually required. Let's say you want to send a data like this 0 1 0 1 1, right? So when 0 is sent, you can say the data line will be low, then again it will be high, and then again it will be low, then again it will be high, then again low, and sorry, then again it will be, sorry, then again it will be kept high, right? Now this is 0, this is 1, this is 0, and this is 1 1. Now you tell me here you have a confusion whether it is the first one or a second one. And then also another thing is there, for how much time you have to keep the line high or low in order for the slave or the master to understand what data it is sending, correct? So to do that, we have a clock pulse. So what clock pulse does, it says for this clock pulse will be continuous. For every clock pulse, there will be a scan happening. It's similar to, I am saying that for every, after every 1 minute, you check what is the status. Now you are going and checking the status, similar to that. So this is the clock pulse. Here the master will check, okay, value is 0, here it is 1, here it is 0, here it is 1, here again it is 1. Like that the entire data will be read. Understood? So clock pulse is required to synchronize the data between master and slave. Okay, so we got an idea why clock pulse is required. It is required in order to synchronize the data between master and slave. Now let's look at the protocol. So why there is a protocol? So whenever there is a like you have how many slave, one two three. So how the master will communicate only to slave one? If I want to communicate to slave one, I don't want to communicate with slave two or slave three, then I should have something via which I can only talk to slave one. So how it will happen? So first master will initiate the start. Remember, always master will initiate the transactions. Okay, here master is controlling the bus, so master will initiate the transaction with a start bit. Then it will have the next 7 bit, which will act as the address of the slave. So this slave address can be 0 cross 1, 0 cross 2, and 0 cross 3. So this is I am writing in hex. So the bits will be filled, and then it will say whether it wants to read from that slave or write some data to the slave. Okay, and then it will start. So this is how the entire process works. Now let me just show you furthermore. Now, few electrical important thing. So I will go into the protocol and now understand why how electrically it is working. So for an embedded engineer, it is also very important to understand the electrical configuration in the circuit or in a protocol. Otherwise, there will be some issues when you want to communicate between two different ICs. Okay, so what happens? These two line SCL, which is for clock, SDA, which is for data. Both are at a high voltage level up to VCC, that may be 3.3 volts, 3 volts, by using some pull up resistor. So these lines will always be at high, and whenever the master wants to do the communication, it will pull down the line to start the communication. Okay, so how the bus is, the bus will always be at a higher voltage. We say it as a pull up, and whenever the communication has to happen or the master wants to communicate, then it will pull down the line and start the communication. Okay, now all the slaves will be connected to the same line, and all the slaves should be having the same ground potential to understand what is the voltage level in the line. Okay, so I hope it is clear that there will be an data and there will be clock. So every data will be synchronized to the clock bits for reading. Now let's go down. So here I am showing you how the slave reads the data, how data is being read from the slave. So here you see, in this, the master wants to read data from the slave. Okay, so this is the SDA and this is the SCL. I can say this is the SCL, clock signal. So with the first clock there is a start bit, the master starts the communication. It will send the address, maybe it can send 0 cross 2 to communicate with the second slave. Then it will send the read write bit, either it will send it set 0 or 1. So mostly for reading it will set it as 0. Okay, nothing, as 0 will be set, and then this data packet will be sent. So this entire data packet will be sent in the first scan, like in the first. Okay, okay, before coming to that, let me just give you one more interesting overview. Okay, so as you saw that there will be a start bit, then data, and then read write. So there will be the start initiated by the master, and then there is an address. This address is 0 to 7 bit address. Okay, so total 128 devices can be communicated. Okay, now, so once the communication once this 1 byte of data is sent, then the master will be waiting for an acknowledgement signal. Okay, so what happens, it's like the master will send 1 byte of data. Which 1 byte? This 1 byte of data, the first byte will be sent. This byte master will be sending, and it will be waiting for the slave to acknowledge it. So what slave will check? Okay, what slave will check it is very interesting. The slave will first check all the slaves. It's not that the first slave, if all the slave, if there are four slave, four all of the four slave will become active and will check. Okay, there is a start bit. Okay, now it will check which address it is having. It will verify this address with its own address. So all the slaves will verify their address. So slave 1 will say whether it's my address, whether it's 01. No, okay, then it's not for me. And slave 1 will say okay, it's not for me. 2 similarly will check whether it's for me. If it's not, then no, not for me. 3 will say whether it's for me. If the address is matched, then it will say yes, it is for me. So slaves will be matching their own address with this address that is sent by the first byte from the master device in the I2C bus. So once this address is verified, then that corresponding slave will send an acknowledge bit. Now what is the acknowledge bit? It is nothing, just the slave will pull the SDA line to 0. So here what happens after this, again the line goes back to high. As we have seen that is normally at a higher pull up, so the SDA line will go high. Now to make an acknowledgement, the slave will just pull down the line to ground. Once it is ground, the master understood, okay, we have received a positive acknowledgement, then I can go forward and start sending the rest of the data. So what rest of the data will contain? It will contain the address of the register from where it want to read or write. Okay, because suppose you say I want to write data, then what question it will come? Okay, from which location you want to write it, or to from which location you want to read it. So first thing will be the location address. Generally it's a general purpose I am saying. It may be some modified case can come, but in normal scenarios there will be an address. After the address, again an acknowledgement bit will be coming from the slave saying that it has received the next 8 byte. Then after that, the data it wants to write will be sent in the next byte and an acknowledgement. If only 1 byte of data you want to write, then after that the entire system sends a stop bit. Now how does the stop bit looks? See here, the start always happens when the SDA is at higher level, is pulled down while the clock is already at high level. Means both of them are pulled to VCC. Now what happens? SDA and SCL. So SDA is pulled down by the master to initiate the start bit. Similarly, here when the clock pulse is already high, then SDA will be released by the master to the high. Then this generates a stop condition and this generates a start condition. Just remember, in both the cases, the SCL, that is the clock frequency, is already at idle state, which is at higher state VCC, and the SDA will be toggled to 0 to initiate communication, and here it will toggle from low to high to makes and stop bit. So just keep it in mind. This is a very interesting, this is a very common interview question, that how a start bit is generated and how a stop bit is generated. So whenever you are asked, just tell when the clock is in ideal state, if a transition happens from high to low, it generates a start bit. And whenever a transition happens from low to high, it generates a stop bit in case of an I2C communication. I hope it is clear. Now let's look back to read and write cycles. So for both reading and writing, we have the clock frequency or the clock pulse generated by the master. Then master will send the read, then it will receive and acknowledge. If it does not receive and acknowledge and receive and not acknowledge bit, means the line is not pulled down. It means you have a wrong slave address, or the slave is off and the slave does not want to communicate. Then you get a anak, that it is failed. Then this next things will not be sent, and the master will, it depends, if after receiving enact, if the master is set to again reinitiate the communication, then it will again start with a start bit. Okay, so here register address will be there, after receiving, so after every byte, means after every 8 bit, there will be an acknowledge signal sent from the slave address in order to acknowledge that it has received the last 8 bits. Okay. Now next thing, similarly for writing data, only thing that will change is the write. So in this case it was reading, let me just clear it off. So in this case it was reading, and in this case it was writing. Everything remains same. After the first byte it will wait for the acknowledgement. So who will wait? Every time master will be waiting. So master will wait for the acknowledgement from the slave device. So if the slave acknowledges, then master sends the next byte of data. That is the address where it wants to write the data. Then it sends the data. It depends how much data it wants to write. Maybe it can write continuously up to uh, 10 data, 10 byte, 20 byte. It depends how much data you want to send. After that, it will stop. Okay. For all these things, the clock pulse has to be continuously sent in order to keep the communication alive. Okay, so this is similar. So this you understood, I think. For every data to be sent, there is a clock bit, and clock bit has to be sent continuously. Now an interesting questions come. Let me see whether I have made that question already or not. So I hope this is clear here. Like the I2C, how the I2C device in network electrically, then the frames. Okay, one more thing here you have to understand. Here the bytes are sent like this, that most significant bit, like it will have the configuration that MSB is first. So you see there A6 is sent first. So if you say 7, so how you write 7 in binary? 1, sorry, 111, right? 7 is like that. Okay, maybe it is not that good. So maybe we write 0 1 1 0 1. So it is 4 2 4 8 12 13. Okay, so when you want to send this data, so how this data will go? First the MSB will be sent, then the next bit. So this is the MSB of this data, and this is the LSB of the data. That is the least significant bit, this one. So every time the MSB will be sent first, then the LSBs will be sent. Just keep it in mind. In this order the data is also sent in this manner. For first bit, which is the MSB, will be sent first in this data, then the LSB will be sent. So every time MSB, then LSB. So this is done, I think. Now let's go move into another thing, that I have put some of the important things that are often asked. You can note it down also. First thing, what are the standard speeds? So our standard speed is 100 kbps is supported. For higher speed, 400 kbps is supported, and even higher it can go up to 3.4 to 5 mbps ultra high. Normally in industry perspective, these two are used, that is 100 kbps and 400 kbps. Now another thing, for 100 kbps the pull up resistors may be of let's say two, if it is 10 kilo ohm, then for 400 it will be of how much? 2 kilo ohm. So these are the some things they can ask, like if it is reduced by 4 times, like it should also get reduced by 4 times. So 2.5 kilo ohms. So these are some basic questions which will be asked. Now why I told you this resistor? This is the pull up resistor. So it will have some value, right? So this value will depend upon the speed of the protocol. Okay, so if the speed of the protocol is high, the resistance value has to be low. Okay, in that manner it is created. Then it is a serial communication. Why? What is meant by serial? Serial means if you have 8 bits, so every bit will be sent one after the another. Okay, one after the another the bits will be sent, right? So it's a serial communication. So next thing is master allowed. Master allowed is unlimited. So why I tell master allowed is unlimited? Because always master will initiate the communication. So there can be master 1 to master n, but it's always that the master will initiate the communication with the slave. Okay, and that particular master can communicate to only a finite number of slaves. So slaves allowed, sorry, so master allowed is infinite, right? Because master doesn't require any addressing, so it will start the communication, it doesn't care about the addressing. So master allowed can be unlimited. Basically it will be always one or two masters in that bus, but technically it can be unlimited. Slave allowed is 127 for 7 bit and 1088 for 8 bit. What is it? It is the address. It based on address. So if you allow an address to get into 1 to 7 bit, so it is 2 to the power 7 minus 1. So it sorry, 2 to the power 8 minus 1, it is 127 bit. 127 slaves can be connected because only 127 combination is possible for the address. Now, one more important thing, that you know that in every IC, how we do so it will be E. So everything is controlled by a transistor. So there is also a transistor that will be controlling it. So this transistor is generally an is in an open drain configuration. So if I say it is base and collector and emitter, so this one is connected to the VCC. Now this is the line, it is like this line is pulled up by a resistor, okay, to VCC. Now suppose this is SDA. Similarly there will be SCL. For SCL also there will be a transistor like this, okay, and it will also be connected to VCC. So now whenever it wants to start a communication, what will happen? So if I make the base high, then it will short circuit this line to the earthing like this, and it will make this potential go from VCC to all the way to ground. Similarly here also it will put it down to ground. So just remember, these are always in open drain configuration. What does open drain means? Here whenever the base voltage is not there or base signal is not there, it is open, and this is connected to VCC. Whenever there is a signal, this is closed and it will be connected to the ground, okay. So this is the about the configuration. So next thing, there are few questions that I have grouped here that are generally asked. So what is a clock stretching in I2C? So interview will ask you, what do you mean by clock stretching? So I will just explain you here. You have a definition, you can note it down. So it is like, suppose there is a master and there is a slave. Now this slave is working at a lower frequency. Let's say this is working at 8 megahertz and this is working at, let's say, 16 megahertz, okay. Now obviously master is very fast than the slave, almost twice, so it will be sending the data at a very high rate. Now the slave needs some time to process the data. Let's say you from the master end, you are saying what is the temperature. Let's say you said temperature data you need, so it will go and convert the value it is having and send you the temperature. In that case, it will take some time to process the data you are asking, correct? So to process the data, it needs some time. During that time, what will happen to the I2C communication? Because once the I2C communication is started by the master, it can only be end by the master, right? The slave can only acknowledge or not acknowledge it. So when the slave is trying to process the data at that time, what master will do? At that time, the slave will be doing the clock stretching. So when slave needs some time to process the data, it will hold the clock, the signal to the ground for some time, which pause the communication. The slave does this in order to process the data for the slave. In this case, fast master and slow slave. So here the slave will just pull the data line to ground, and it will sit there until it does the calculation inside it, and then when it is ready, it will again start sending you the data, right? So this is what the clock stretching is. So next question is, what is bus arbitration in I2C? So this question will come when there are more than one master in the bus. So you have an I2C bus with two masters, okay? So you have this bus and you have multiple slaves connected, S1, S2, S3. Now This master doesn't require to have an address, but the slave does, right? So what happens if both the master wants to communicate at the same time? So there will be a conflict, like who will do the communication. In that time, to resolve that conflict, there is an arbitration that will happen in I2C. So it is the mechanism that will resolve this conflict. So what will happen? The master will constantly monitor the SDA line. Whichever master sends zero first will win the arbitration. So it is very clear. Both of them will start communicating at the same time, right? So let's say this master will start sending this, both of them. One master wants to communicate with 010, another master wants to communicate with 012. So let's write the binary of 2, that is 01, and what is the binary of 1, that is 1, right? So what it will send? It will first send the start bit. Both of them are sending the start bit. Then it will send the address. So I told you the address will be in which order? It will be in your MSB first. So first MSB, it will be sending 0. So there will be all the bits up to 7 bit. It will be sending to 0 0 0 0 1 2 3 4 5 6 7, and here it will also send 1 2 3 4 5 6 7. Now whoever sends the 0 first will win. Now here both of them are sending 0, that is okay. Up to this bit, that is the sixth bit, everything works fine. Now next time when this sends a 0 and this sends a 1, then it fails, right? Then this master M1 wins the arbitration and M2 stop sending the data, and then S2 continue, this M1 continues to communicate. Once this data line, that is SDA line, is again pull up, and there is no clock pulse being sent continuously, so that time again M2 will start sending the data. So this is what happens. This is called an arbitration, where if there is two master, then one master will take over the communication whenever both of them starts to communicate at the same time. Okay, so now, okay, let's go to the second thing, that is what is priority in I2C bulk. This also comes from the thing that if there are two masters, then there is also saying that there is also a priority. So priority, it is determined by address and payload. The lower address has higher priority over the higher address. So if there is a concept of priority involved in the I2C bus for both the master, whichever master has the lower priority will win. So here you see here, sorry, whichever master has the higher priority will win. So higher priority is meant by the lower should be the address, and uh, lower address will always win over the higher address. So this is the priority. Here also you saw this, right? So if you are saying this is 2, so you are sending 0 will be first. So higher address means what? So the MSB will be filled first, and always we are sending MSB. So if the MSB is high, so generally it is like, let's say you are right 1 0 1, so this is 3. Now you write 1 0 0. So I told you whoever sends 0 first will win. So here the first bit is 1 and here the first bit is 0. So this is the address of 2. So 2 will always win over 3. So this is here nothing but the priority in I2C bus. In arbitration, the priority is always the lowest address wins first. That's it. Okay, so I hope I2C is clear for now. I will make another video for UART. So if you have a doubt or a question in I2C, just ping me in the comments. I will reply it. Okay, thank you, bye.